Good afternoon, everyone. Welcome to our virtual informal systems seminar this week. We have our speaker today, Derek Onken. Mr. Duncan is now a current PhD candidate in the Computer Science and Informatics program at Emory University, and he is advised by Lars Rutherto. Prior joining Emory, he received his bachelor's degree in mathematics and computer science from the University of Georgia. His research examines design applications of neural differential equations. In addition, Derek enjoys applying machine learning to applications arising in the health industry. He recently published a paper which uses cell phone billing records for privacy preserving epidemic surveillance. He did internships with the US Air Force Research Labs and the United Health Group R&D, where he applied machine learning methods to toxicology and lung cancer detection. He recently accepted a position at Eli Lilly and Company. Today, his talk will be on the application of neural networks to solve problems, optimal control problems with higher dimension. So without further ado, let's welcome Mr. Onken. Derek, the floor is yours.
Awesome. Well, thank you for that introduction, Shuang, and thank you to all of the organizers for this seminar, for the invite. I guess we'll just hop right in. Feel free to ask questions kind of throughout. That's how my department does it, and we should be really good on time. So first, I'd like to thank my collaborators. This work is kind of a joint venture between Emory University and UCLA. In particular, I think you guys know Levon. He has some McGill ties. He was very taking the lead, I think, on a lot of the optimal control aspects of this work, and I want to give him a lot of credit for what we ended up with. A little overview about what we'll talk about. First, we'll do a little background about optimal control problems. Sounds like most of the audience knows more control than I do. Then we'll talk about some mathematical formulation of how we set up the problem and our neural network approach. And then I'll show you some pretty videos, and that'll be it. So we'll motivate everything from this simple four-dimensional example of this problem where we have two agents kind of in the bottom left and right hand corners, and they're trying to get to some target locations on the other side of these two hills. And these two hills have some sort of valley or corridor in between them. And we want the agents to figure out a way that one agent will go through first, and then the next agent will go through, and trying to teach a model or a neural network machine learning model to learn how to solve this problem. And so then we'll get into some other aspects of the problem. But of note is each agent has some sort of radius, has some sort of space bubble around it, and we want to make sure that those specifically aren't overlapping. We assume we have control over, for this case, the agent's velocity, but we use a more generalized framework where we just have some control. We want some optimality. So for this case, we want shortest path, some sort of geodesic to make sure you're going around the hills instead of over them. We want to make sure we have no collisions. We want to make sure the agents reach the target. And this is kind of just one small example that we're going to use to motivate most of our work. So in this example, we would take the agents and stick them into some sort of joint state framework. So imagine in general, we would have n agents that are in some sort of two-dimensional space. And if we stack them all up, then we have a d-dimensional state that we're dealing with throughout the problem. So for this case, agent one starts at like -2, -2. Agent two starts at 2, -2. That would be the initial point, and then the target point would be 2, 2 for target one, and then -2, 2 for target two. And the path that they're going to follow from like time 0 to some sort of fixed final time, capital T, will be mapped by Z. So Z is going to be our trajectories or our state associated with some initial condition X. And so technically Z is a function of both space and time. We don't really use the space too much, but it's important to kind of hang on to it. So that's why we use this little sub notation here for X associated with Z. And at the final time, we want to make sure that our agents are reaching the target. So we have this loss function G, which is kind of the agent's position at the end of the trajectory, subtracted by the actual target, and it's just L2, and we have some sort of weighting parameter alpha1, which you tune when you set up the problem. And we'll talk about that more later. So the trajectories themselves are governed by some differential equation. Here, the differential equation is F. For the corridor problem, it's just the velocity. The velocity is the control. So we have our state or trajectory Z, and we have the control U, which is also like dependent on the initial condition X. So we keep using that little X notation for that. And that's pretty much the differential equation we're dealing with. So then we also want to include all of that optimality and collision avoidance. So we set up a running cost for the control problem. Running cost is L. And so it's a sum of some sort of energy term. So for the corridor problem, this is going to be just the arc length of the trajectories. And then we also want to include the obstacle or terrain function Q. So in the corridor problem, this is the two hills we have there, which we usually incorporate as some sort of just some of Gaussians. And then for the interaction cost, we'll call that W. And for that, we always use some sort of piecewise Gaussian repulsion function. So if you have agents Zi and Zj, and the idea is, okay, you have their space bubbles. When the space bubbles overlap, you want them to kind of repel or away from each other. But when they're just side by side, then you want it to be 0. And so that's kind of the idea. When the radius between the center, like when the radii of these space bubbles overlaps, then you kind of activate this this repulsion function here. And we assume that all of our agents are homogeneous and the interaction cost is symmetric, but that doesn't need to be true in general. It's just what we chose for this interaction cost. Now, in optimal control problems, a lot of times you're looking for this minimal cost, phi. So that's what's going on is between your starting point Z or 0 and your final time capital T. You're at let's imagine you're at some point little t in your time horizon. Then you need to figure out, okay, how much cost do I have remaining to get from my current point to my final time capital T? And so that cost is your cost to go. And that is the sum of kind of your running cost from your current point to your final time. And so we just integrate over that trajectory you would take, plus your kind of your terminal condition, how far away you are from your target at the end. So at any time little t, then you would have kind of like this cost to go, and you want the optimal cost to go. So you want the control that would lead to the minimal cost to go. And so that's just the value function. And the value function is the holy grail in optimal control problems. And so we're going to talk more about that. And the solution that solves this value function, that gives you the value function, is the optimal control. And the resultant trajectory from applying that strategy is the optimal, that's the optimal control. And the trajectory that comes from that optimal strategy is the optimal trajectory. So a couple ways people solve these problems. We're just going to talk about two. One is kind of this Pontryagin maximum principle approach. And that essentially boils down to solving this forward-backward system of equations, which can be kind of a pain to do in practice, but it scales well to high dimensions. So some of the comments there are, it's a local solution method. So that means if I give you one initial condition X, and then you solve this, but then if I change the X for it, then you're going to have to resolve the whole thing. Theoretically, you could restart with kind of like your solution to the other one, and that might help you solve the problem. But that's also leading into kind of the next point, which is that solving the system, it's difficult because of the forward-backward nature, but it also depends on this initial guess. So this was, if we were to use a shooting method, then it depends on kind of your initial guess for the adjoint. And so we won't talk too much about this, but that's one method, one approach. Another approach would be to solve the HJB conditions, HJB equations. So this is a PDE that we know that phi has to solve at optimality. And this is great because it's a global solution method. So if I change the starting point X on you, you can still use the same phi now that you know what phi is. The problem is this doesn't scale really well to high dimensions. So this is usually called the curse of dimensionality because you usually need grids to kind of solve this equation in high dimensions. And there's a lot of work on more efficient ways to do so, but a lot of them are still bound by this curse of dimensionality, where your costs exponentially increase as your dimensionality D increases. So what we want to do is we want to kind of take the benefits of both of those approaches and combine them into like one method. So we're going for the semi-global solution method, where if you change that initial condition X, then you could still use the same model, the same approximation for phi, which is what I should, little foresight, we're going to parameterize phi with a neural network. So then we're going to have some model for the value function. And if you just reuse that value function, you can use it even though you have multiple initial conditions, like I'm showing here in this video. And the other aspect of that that's important is if there's some sort of shock or disturbance kind of along the trajectory. So if you get halfway through, your agent is proceeding and then there's some sort of, I don't know, wind blows you off course or you get pushed out of the way or something, then you can, you don't have to recompute. You can just use the phi you already have and continue on to your target. Remember the issue with HJB was that it doesn't work well in high dimensions. So that's where we're going to leverage the neural network aspect so that we can scale to higher dimensions. And we're going to use some of the benefits from the PMP in order to do that. Now, our motivation in all of this work was really to solve high dimensional optimal control problems. And we got to the point where we didn't really have too many high dimensional optimal control problems, just kind of sitting around that were 100 dimensions or so. So that's why we kind of shifted to doing more multi-agent problems, because it's easier to see kind of the high dimensions in more of a framework. And that's how you can evaluate how the model's working and whatnot. And so that's kind of where we ended up with a lot of these multi-agent works, but we're solving them as like centrally controlled agents. So we want the semi-global phi. And so the way to do that is we usually solve for the Hamiltonian H in our problems. That's, our approach is set up generally, but for some aspects, solving the Hamiltonian might not necessarily work too well, or you're going to need some fancier tricks. Then after you solve for the Hamiltonian, you replace the adjoint with grad phi from one of those previous equations. And then we're going to use a bunch of initial states kind of sampled from a Gaussian distribution. Doesn't have to be Gaussian, we just did Gaussian. But so here it would be like, okay, we're going to sample all of these kind of initial positions for agent 2 here. And the idea is then when you have some sort of shock or disturbance kind of like part way through your trajectory, the model can just take it in stride and continue pushing the agent towards the solution. So then we're going to reformulate kind of that loss we were talking about, or that objective function. And it's going to be this expectation value of all the states that we are sampling. Okay, and again, we're trying to find, we're going to change out minimizing for the control for just minimizing for the phi, which we're going to replace with a neural network. So here we're solving basically this minimization problem with respect to this ODE. And so there's a more generalized form, but this is specific to the corridor problem, where we said that our dynamics are just the velocity itself. And in doing so, we also want to incorporate more of the HJB that we understand. So at optimality, the phi that we're going to arrive at should hold true for this PDE. So we can take that and we can turn it into these penalizers. So this is like this first equation becomes this HJT penalizer, which has been used in a couple other works. And this isn't even all the works where it's been used. But so what people have tend to find is that this penalizer leads to fewer time steps. And that just kind of makes the cost simpler when you're training your neural network. The terminal condition turns into this HJ final time penalizer. And then we can also use the transversality conditions, which is just the gradient of that terminal condition. Yeah. So then we have these three penalizers. They look confusing. They're not necessary in the problem because they don't actually change the solution. My easiest way to kind of explain what they're doing is they're just speeding up convergence. So this is if we're like training a model over 2,400 iterations. When we use the penalizers, we tend to converge much quicker to a solution than if you don't use the penalizer. Or if you use weight decay. Weight decay is just taken off regularization, but computer scientists like to come up with fancy names for things. So penalizers don't actually change the solution mathematically. They just kind of help the model search go through the search space much smoother and quicker. And so that's the idea behind having the penalizers. And we're going to include them in the equation like this. So now we have these three penalizers, and we have these kind of more weighting on them, these betas. And those are going to be called hyperparameters of the model. And they just kind of weight the importance because you don't want this penalizer to be more important than actually like solving the problem. So these betas can range in value, but usually they're pretty small, and it's all relative to the problem setup, which was the previous alpha values we had talked about. So a couple other things here. We've added the penalizers in, and then we've turned those time integrations into just aspects of the ODE. It's the same thing, but that integral with respect to the running cost is now here, and the integral with respect to the integral for this HJT penalizer is now here. Okay, and this is the problem we're trying to solve. So then I ask you, how do you solve this PDE constraint optimization problem? And the answer is really you blend neural networks and differential equations. You can choose your buzzword. Some people say neural ODEs. Some people say physics-informed neural networks. Really doesn't matter. They're all kind of the same thing. And I'm sure people have come up with more names, but that's kind of the name of the game. So now I'll talk to you a little bit about kind of neural network basics for those who might not know too much. A neural network is just a parameterized function, as we would say in math. So in this example, imagine my input is some d-dimensional vector z. That was the state of the system. And then the output's going to be capital C. And it doesn't, these dimensions don't actually matter. They're just relevant to our actual application because we're going to essentially parameterize phi. So you have some input d, output is scalar, and then you have some parameters or weights of the model, which is denoted by theta. So what neural networks tend to do, they're a parameterized function and they're a concatenation of a bunch of smaller functions. And the idea is really you have some sort of input features, you project them onto some manifold in a higher dimensional space, and then you do that a bunch of times, and then you kind of end up with whatever manifold you want at the end. And you tune the whole thing, it's all parameterized, so you have some loss function that you're minimizing, and you tune the parameters to do this the best way to your liking. Okay. So here's like a simple example people like to show. In computer science, people show all of these fancy ball and arrow plots. We like to stick more to just kind of like math because it's just matrix multiplication, and then you have this nonlinearity. Originally, people were talking about neural networks. They were thinking about the brain and neurons and some sort of pulses going through that could be represented by a step function. Then they said, oh, well, we can't take the derivative of a step function. So then you end up with these kind of curved looking step functions. And that's the nonlinearity here, this sigma that's being added in the hidden layer. These are all fancy terms, but the idea is you just do matrix multiplication and then a nonlinearity and then more matrix multiplication, and then you combine a bunch of these together, and that's your neural network. So here we're just doing, this is one layer, matrix multiplication, nonlinearity, and then another multiplication. And so then we kind of build our network from here. So this would be our one layer, and our input is going to be space-time. So the layer itself is going to operate on a d+1 vector, which is just kind of the current state it's at plus the time, or I shouldn't say plus, concatenated with the time. And then we include another layer in this kind of formation, and this is called a two-layer Resnet. And Resnets were kind of a really big thing that came on the scenes in 2015 and 2016. And they were shown to be super effective in image classification tasks for self-driving cars, the COCO dataset, ImageNet, all of these. computer vision tests, right? And so we have this simple Resnet, and then we kind of add, we do another matrix multiplication and add a quadratic. So this is our model then for phi, okay? So we've now parameterized the value function with this model. And here's all of our parameters. And I know it looks scary. The reason I wrote it out is because a lot of times in deep learning, you actually can't write it out when you have 100 layers or 200 layers or something too complicated to really visualize. But I'd be happy to answer any questions people have about this stuff. So now let's step back to our PDE constrained optimization problem, which was this. And what we're going to do is we're going to include now our neural network in for phi. So then what happens is we're going to minimize over the parameters of phi. Now, instead of phi itself, we've replaced phi with the neural network, and we're going to minimize the parameters, minimize with respect to the parameters of the neural network, such that we're still kind of solving the same problem. And that's our neural network. So then the idea for training this neural network or neural ODE, because this is now an ODE that depends on a neural network layer. We go through kind of 4 steps of training the neural network. So what happens then is you solve the ODE in time, then you compute the loss function, then you do what's called backpropagation, which is just chain rule, and then you'll update the parameters, and you'll just do this however many times you want to, or until you reach some sort of stopping criteria. So for us, we just kind of set max number of iterations and saw if the problem worked well or not, if the model trained well. So for the solver, we use Runge 4 to solve the ODE. This is usually efficient and accurate. We are able to solve most of the problems with just like 20 time steps. Then we also were using the discretize and optimize approach. So you're discretizing the ODE at time points, and then you're optimizing over that discretization. And so then you have some concerns about overfitting to the discretization, but in the validation step, we would do a different discretization to make sure that we were still solving kind of the continuous problem. And the other way people tend to do this is the optimize and discretize approach. So they'll solve the adjoint equations. And then you kind of have all sorts of other issues that arise that are kind of addressed in these 2 papers. And then for computing the loss function, it's pretty simple. You just compute it. And then for backpropagation, we use automatic differentiation, which is standard in a lot of the machine learning packages. But basically, it will do the chain rule for you because they have this kind of library of functions. And then as you've done your kind of evaluated your forward model, you know which functions you've gone through, and then when you tell it to do the backpropagation, it'll just do chain rule for you. It's really great. If you don't use AD, I recommend that you do. So that's how we get the gradient. And then for updating the parameters, we'll use Atom. So the parameters, I mean, I wrote out the parameters for you. They can tend to be, we're talking 1,000 parameters to 300,000 are kind of that's the range of number of parameters we've been working with in our problems. So this is a pretty high dimensional search space, and you're trying to find some sort of minimum in that search space. So that's where the penalizers come to help you out so that you can traverse that search space much easier. It's also very noisy. It's non-convex. So Atom works pretty well. We did some work using like BFGS and some other, more standard optimization techniques. They work well too. Atom works like 1% better, so that's why we stuck with that one. But that's how we solve the problem. Now we'll talk about some results. So for this corridor problem, we've solved the problem kind of on a space. And the idea was to be robust to any sort of shocks or disturbances that you might see along the way. So in these experiments, we apply some sort of random noise, essentially. We just add some vector to whatever state you are about 1/10 of the way through and see if the model can still solve the problem. So here for these smaller shocks that are still kind of within the realm that we were training for, the problem still solves it, or the model still solves the problem, and the agents reach a solution, and they do so pretty close to optimally. For really large shocks, like this one here, where you're shocked to kind of a joint state that's way out of the range that we were training on, it'll still solve the control problem, but it won't do it optimally. So we have a baseline, which I'm going to talk to you on the next slide, that would kind of send this agent around the left side. So you lose some of the optimality if if you see something you haven't expected before, but you would still solve the control problem, which is a drawback or a limitation of the approach. The way you would fix this in practice is you would just make sure you're training on kind of the whole space. You would be training on points over here if you expected some sort of shock to happen that would shift you over to that space. The baseline itself, we just did kind of a discrete optimization approach where we used forward Euler to solve kind of the loss, the initial loss and the time integration of the running cost. So this would be one way to solve the problem. And then your controls in this approach are the velocities themselves. So you just every time step you do, you are told which vector to head in. Now this is a local approach like the PMP, and when we are doing a lot of the comparisons, so for one figure that's supposed to be in like the next paper, we were comparing essentially 10,000 of these baselines, because they're all local, to like one neural network. So if I give you 10,000 initial points, how does that look? How would that be solved relative to the neural network? So the results were pretty good, but I don't have that figure here. So here I have this one example. You can see we lose a little bit of optimality when we're solving it globally, and that's because the trajectories that the global neural network is learning is that you send through agent 2 first, and then you send through agent 1. So then agent 1 is kind of like waiting, and this would be kind of like all of the states that we had sampled around here versus like all of the states we sampled around here, right? And that's kind of the idea there. Next, we shifted to some other problems that existed in this other work. So here, this is kind of a hard boundary obstacle, which we relied more on that piecewise Gaussian approach we had done for the interaction cost. So what's going on here is the obstacle in here when we train is still represented by a Gaussian. And so then if your agent were to go over it, then you have gradient information to kind of push it out, push it away from the top of that hill. But then we have kind of like a piecewise formation, so that then if you're like the Gaussian's only evaluated within that kind of boundary. So those hard corridors, we can do that. Anything with a hard boundary, we have a way to solve that problem. It just is a little bit more complicated. And then here we have another case where these agents are swapping positions. So this is 6 pairs of agents, and each are kind of swapping positions with each other. So this like green and red one are swapping places with each other across the same time. These 2 are swapping places with each other. These 2 are swapping places with each other, and so on. And this one's my favorite because I always see something new that's very interesting. So you see like this one's going the wrong direction at first, so that then this brown one can come down. And so this is just one of the solutions from the neural network, and it's solving it on many initial conditions. So this is just one initial condition shown here. So this also kind of led to maybe we wanted to assess how our model was handling the cursor dimensionality. So from that kind of that 12 agent problem, remember we have 6 pairs of agents that are swapping positions with each other. We wanted to kind of sit down and figure out what's a good way to address how our model scales with dimension. And so Laban and I in particular really discussed like, okay, what would be kind of a convincing argument that our model is handling cursor dimensionality. So here we're controlling kind of for as much as we possibly can. We have the same general framework of problems, but we'll have one problem that's kind of 2 pairs of agents swapping across each other, then 3 pairs, then 4 pairs, and 5 pairs, then that whole, like the 6 pairs of agents that I was just showing you. And for each one of these problems, we trained a neural network, and we would see what is the smallest neural network we can train that still achieves a fixed amount of suboptimality relative to the baseline. And so then this is what you come up with. So for these smaller dimensional problems, you only need about 200 parameters in the neural network in our framework to solve the problem. And then it linearly grows up to a little under 1,000 for the 24 agent problem. Now, that's for kind of solving these different dimensional problems. And in the meantime, we also looked at kind of training time, which is, it has some limitations because we trained everything on a GPU, which does a bunch of parallelization. But you can see that the training time doesn't grow exponentially, which is kind of the concern a lot with that cursor dimensionality. So we really like those results, and we're going to include them in kind of an upcoming paper. And then we stepped onto another problem. So this is where we really wanted to kind of build up and do even higher dimensional problems. So here, this is kind of a swarm. So you have these 3-dimensional agents. We have 50 of them, and we want to have them all move from one side of these one side of these obstacles to the other side, and they have to kind of go around these obstacles that we just did some rectangular prisms. So here's kind of a nice angular view, and then here's kind of a side view if you didn't believe this angular view. But basically all 50 are going to their target, and they're not colliding with each other, and they're not colliding with the obstacle. And it's really easy for us to tell that computationally, because we just compute those interaction costs and the collision costs, the terrain costs. So the Q and W, we can look at those, and since they're exactly 0, then we know, okay, it's avoiding everything. So that's all well and good. But then we asked, okay, what's something that's like more realistic? So more realistic example would be where you have control over something else, not velocity, but in here, usually some sort of acceleration. So for the quadcopter, quadcopter is a 12-dimensional object in the sense that you have kind of XYZ position, and then you have this pitch yaw roll, which are these kind of like angular positions relative to the XYZ Eulerian coordinates. So that's kind of your 6-dimensional state, but then you also have the velocities for each of those 6 dimensions. So that becomes really a 12-dimensional state for the quadcopter. And you have 4 controls. So you have the thrust, which is kind of like the force that's lifting the quadcopter. And then you have the 3 torques around those, the pitch, yaw, and roll that we were talking about. So here are the dynamics that we took from this paper, Creo et al. And we wanted to see if our neural network could solve that problem. And what we would do is we would just start it from some point and see if the model could get it to some sort of target position. So the baseline would look something like this. A neural network, remember, works on a global setting. So then for any of these initial conditions, this is how it would solve the problem. And you can even look at a comparison here of the controls themselves. So the neural network and baseline are learning very similar strategies for how the quadcopter should function to get from initial point to target. So in review, we wanted to solve these high-dimensional control problems. We wanted to solve them semi-globally. And so we were kind of combining the benefits of the PMP and the HJB, and we parameterized the value function in order to do that. And we were able to solve a trajectory problem in up to 150 dimensions and solve this quadcopter problem that had more complicated dynamics, more realistic problem. And we also demonstrated some of the shock robustness capabilities of our model. And some of the conclusions then are like parameterizing the SPI led to a lot of great extrapolation capabilities. So that's when we're talking about when you had a shock that was outside of what you trained on, it still solved the problem, which is novel in the sense of neural networks, because neural networks are well known for extrapolating poorly. Since it didn't optimally solve the problem, I would like to mention that that is a limitation. but it is still solving the control problem, which we thought was very impressive. The ISS Finalizers, they improve training, but they're not necessary to solve the problem. And then the Lagrangian coordinates we were using, since we're integrating everything over the paths themselves, allowed us to scale to higher dimensions without the need for grids. And so most of that was presented in kind of this work, which is on arXiv. And we found out this morning it was accepted to the European Conference on Control. So that was great news this morning. And then we have another kind of paper in the works of a much longer work that includes some of the additional experiments I was showing and has a lot more kind of insight and description about the method itself that we're hoping to push out in the next coming months. So I don't think the code's public yet, but the simulations, like the videos I showed you, those are all online if you have any interest in that. So some of the future work is we'd want to do some more vigorous experiments. So we've done one 12-dimensional quadcopter, but it'd be interesting to do more 12-dimensional quadcopters with more obstacles and whatnot with these complicated dynamics. And I know at least one of us has a lot of interest on deploying on actual quadcopters. So working with engineers to test the method in reality. So one of the papers we cited there with the swarm problem, the Honig paper, they are more engineering, and they have actually, like, their paper was, oh, look, we deployed it on 50 quadcopters or 32 quadcopters in a room, and this is the video of them working. So we would be interested in doing something like that. We also want to do some combination with existing methods and sensors. So the drawback, again, our motivation was to solve optimal control problems in high dimensions. And the easiest way to develop those high dimensional problems was to do multi-agent problems. But in practice, there are a lot of concerns about solving a multi-agent problem in the joint state, because then you would have to figure out communication between each other. And then imagine there's like a bird that flies through, then you would need to have some sort of sensor and existing methods that kind of handle kind of unexpected obstacles that might show up. So those are kind of some of the future work directions we're working on right now. And with that, I'll take any questions you guys have.
Thanks, Derek, for the great talk.